Hello everyone, nice to talk to you all. So this class we're going to continue our topic on the fundamentals of environmental engineering and science. And specifically we're going to talk about the DO Sag curve, which is the dissolved oxygen Sag curve, and also water quality in other water resources. Okay, so first let's do a quick recap of our last class. So last class we learned about what BOD is, or the biochemical oxygen demand is, and also how it is different from the COD and the theoretical OD. COD is chemical oxygen demand, and the theoretical as a chemical oxygen demand and theoretical oxygen demand is basically based on the chemical formula of these organic species, right? Also, we learned how do we experimentally determine the BOD. There are several steps. Normally, we'll use the BOD bottle, and then just to measure the dissolved oxygen concentration after maybe 5 or 7 days. And also, why do we normally dilute the wastewater? This is because normally the wastewater is going to have a high BOD, which is not survivable for the microorganisms to oxidize these organic species. So we have to dilute them so that it still contains enough dissolved oxygen for the microorganisms to survive. And finally, how do we correct the oxygen consumption of the seeding bacteria? And this is done by setting up a control group, right? So in last class, we basically assumed that only the carbons or the hydrocarbons are going to get oxidized. But actually, in the wastewater, there can be a lot of nitrogen-containing species. For example, the proteins and also a lot of the consumer products also contain these nitrogen species. And therefore, we further divide these BOD into carbonaceous BOD, which is a CBOD that we learned about in our last class, and we learned that we can experimentally determine the CBOD from the wastewater. And there's also nitrogenous BOD, which is NBOD. Okay, the reason why we separate them out is because the microorganisms for oxidizing these carbonaceous species are largely different compared to the microorganisms that are oxidizing these nitrogenous species. Okay, so they are oxidized by a special group of nitrifying bacteria. So therefore, when we consider about how the organisms are being consumed, these special group of bacteria are going to have a delay time in terms of their population, because they are normally they'll have to wait for the larger carbonaceous groups to get dissolved first so that nitrogen species are available to them. So if we learn about the chemical process of this reaction, so basically these microorganisms are going to utilize the ammonia ions, the ammonium ions, and these ammoniums are oxidized by these oxygen, and then to form these nitrate ions, water, and protons. And from this reaction, we can calculate what is the theoretical NBOD, right? So again, this is going back to the theoretical BOD, right? So from this chemical reaction, we can find that for each gram of this nitrogen that's being oxidized, we can calculate or find out that it needs 4.57 grams of oxygen, and which actually is a quite large amount of oxygen, right? And actually, in the river water and in the wastewater processing, this actual value or the BOD value, NBOD value, is slightly lower compared to the theoretical value. And this is mainly because some part of these nitrogen or ammonium are converted into the body of the microorganisms. Okay, so they're not everything, so not all of them are being oxidized to these nitrate ions. Okay. So with this information, we can plot out what is the BOD as a function of time. So last class, we showed that why the CBOD, or the normally measured BOD, will have a curve that looks like this, right? This is mainly because if we want to calculate the BOD value, that's decided by this equation, L0, which is the initial concentration of the organics, or the ultimate BOD minus this concentration of the organics at any time, And this is going to provide us a curve, or the reversed exponential curve. And as we have introduced, for the bacteria or microorganisms that are oxidizing these nitrogen species, normally there will be a delay time. Okay, so because of this delay, the NBOD are going to build upon the CBOD. Okay, and you can also see that this amount is relatively or quite considerable compared to the CBOD for the untreated sewage and the treated sewage, right? And also we can find out that for the treated sewage, they have much lower BOD values compared to the untreated sewage. So that's why for a lot of the chemical plants or for the residential wastewater, we have to treat them first before we dump them into different water resources. And this is the reason why we want to understand first how the BOD or how this wastewater are going to affect the oxygen or the dissolved oxygen in river systems. Okay, so let's think about an example. So for example, you are an environmental consultant of a chemical plant, right? So chemical plant, of course, they want to make money, so they cannot convert all of their wastewater back into drinking water. So there's always some pollutants in their wastewater there, right? So they decided to build their plant nearby a river, and then for these wastewater, they will use these pipes to dump them directly into the river. Maybe there are some treated process, maybe there are not. So what's going to happen to the ecosystem or the dissolved oxygen in the river? Okay. So one thing we know for sure is that upstream of this pipe here, there may be some diverse lifestyles or the diverse diverse organisms in the water. So basically there are a lot of fishes, there are insects, right? Because the dissolved oxygen concentration is high. And then once these wastewater mix with the upstream river, that's going to cause a decrease of the dissolved oxygen in the water. And as we have introduced earlier, the lower the dissolved oxygen, the more difficult for these higher level of organism to exist. So this is causing the dissolved oxygen concentration to decrease. And this is because we're oxidizing all of these organics in the water. So the fish disappeared. There might be some insects still, but there are a lot of microorganisms. And these microorganisms are oxidizing these organic species that's in the water. And one thing we know is that this concentration will not keep at a very low value. And this is mainly because in the atmosphere, there are a lot of oxygen molecules, right? So these oxygen molecules are being actively dissolved into the water. And let's say if there are more turbulent flow taking place, right, and the flow is also very active, then it's further easier for the oxygen to dissolve into the water. So there's always some oxygen being supplied into the river. And as we consume all of these organics that's being emitted into the river, the oxygen concentration can go back again. And of course, not only the oxygen can dissolve, but also maybe in the river there are some green plants, right? The plants will also generate oxygen and they can dissolve into the water. So as the dissolved oxygen concentration increase, all of these different levels or different forms of organisms will reappear. We're going to have the insects and the fish again. Okay, so if we plot out the biochemical oxygen demand or the BOD, you can see that at this mixing point the BOD is 0, and then as time goes on the concentration or the BOD will keep increasing, and then finally it's going to reach this plateau here, and we call this value as the ultimate BOD, which is introduced in our last class. So now you can see that the concentration of this dissolved oxygen is mainly affected by two processes, right? So the first process is the oxidation process that's reducing the oxygen concentration in the water. And the second process is the this replenishing process. And we also call this process as the reaeration. Okay? So these two processes are basically competing for the dissolved oxygen concentration, and this is going to give us this curve here, and we call this as the dissolved oxygen or the DO Sag curve. Okay. And further, if we look at the rate for these two processes, let's say the oxidation rate or the deoxygenation process, which is reducing the dissolved oxygen concentration in the water. You can see that the rate of the deoxygenation should be proportional to the concentrations of these organic compounds, right? So basically, the more polluted species that we dump into the river, then the higher the rate for this deoxygenation. All right. And in terms of the reaeration, you can see that the rate of this process is going to be proportional to the how far the oxygen or concentration is deviated from the saturated concentration. Okay. So we see that this rate is proportional to the oxygen deficit. So basically, the oxygen deficit is normally we'll use the parameter D here. It's calculated by the saturated dissolved oxygen concentration minus the current dissolved oxygen concentration. Okay, so we call this parameter as the oxygen deficit. It is reversed compared to the dissolved oxygen concentration. So basically, the higher the deficit, that means the lower the dissolved oxygen concentration, right? We can also find that the highest oxygen deficit is going to be equal to this saturated dissolved oxygen concentration, which is around 9 milligram per liter. Okay, and also the lower the oxygen deficit means that the more pure, the more or the cleaner the water is, because the lower the D, that will be the higher the DO, right? So it is reversed compared to the trend of the dissolved oxygen. Okay, so if we further plot out what is going to be the dissolved or the oxygen deficit in this river, so that's going to be something looks like this, right? Okay, so finally the oxygen deficit is going to go back to zero, and then initially the dissolved oxygen concentration or the oxygen deficit might be low too. Okay, so from a more mathematical way of looking at this process, so this is plotting the dissolved oxygen concentration in the river again. Okay, so you can see that there will be a decreasing trend, right? Initially, this is because of the deoxygenation that's coming from the oxidation of these chemical species, and then because of the aeration or the rate of the aeration is higher compared to the deoxygenation, then the dissolved oxygen concentration will increase again. But if we look at these different points, you can see that initially the dissolved oxygen concentration is not at the maximum. Why? This is mainly because we're talking about this Sag curve that's coming from the initial point here, right? So at this initial point, the mixing take place, okay? And because of this mixing, in the wastewater, the dissolved oxygen should be low. That's because there's a high BOD value, right? And because of the mass balance, right? Although the dissolved oxygen here might be really high or saturated, once they're mixed, the dissolved oxygen concentration will become lower. So it's not at the saturated condition. And then it's going to reach to a minimum, right? As we have also seen here. This is mainly because initially the oxygenation rate is so high, right? So we call this process, we call this point also as the critical point. And then after the critical point, we're going to observe a continuous increase of the dissolved oxygen concentration. Okay? Then how do we solve for this Sag curve here? So how do we mathematically predict where is, for example, the critical point and how fast the dissolved oxygen can resume back to normal? So what we're going to use is the concept that we learned in our earlier classes, which is the plug flow reactor. So if we can think of this river flow as a pipe, okay? So the river flow is going this way, right? And the reaction is only taking place in each slice here. Okay, so there's no reaction or there's no mixing before and after this imaginary boundary here. Okay, so all the reaction is taking place in this slice here. So now we can try to build up what is an equation that's describing this thin slice. Let's say that we decide to choose this slice, which is at location of x to x plus delta x. Okay, and we're trying to build a relationship based on the oxygen deficit. Okay, so then what we can say is that the oxygen deficit at x point at the location of x multiplied by q, which is the oxygen deficit flow into this thin slice here, okay, minus the dx plus delta x multiplied by q, and this is going to be the reaction rates. Okay, so basically, let's say if initially the oxygen deficit is high, and then after it travels for delta x, the oxygen deficit becomes lower. Okay, it's plus delta x and x, and this is mainly because of the reaeration rate. The rate of the reaeration is higher compared to the rate of the deoxygenation, right? So then we can write out the other terms, which is Kr multiplied by V, okay, and also multiplied by the oxygen deficit that's within this thin slice here. And also we need to consider about the deoxygenation, which is Kd multiplied by V multiplied by L. Okay, so we have introduced that the rate of the deoxygenation is proportional to the concentration of organics, while the rate of the reaeration is proportional to the concentration of the oxygen deficit, right? So now what we can do is that we can try to limit what is the equation here, okay? So we can find out that V here is basically equal to S multiplied by delta X. Okay, that is the volume of this thin slice here. So what we can do is we can take out the Q and then minus, basically minus dx plus delta x minus dx divided by delta x. So basically we move this term to the left hand side. Okay, that's going to be equal to Kd Krd multiplied S minus Kd L multiplied by S. Okay, so further we know that for the flow rate, that's equal to S multiplied by the velocity of the flow rate, right? So we can write out this equation. We can further move this S term to the left hand side, which is minus Vx dx plus delta x minus dx divided by delta x is equal to Kr d minus Kdl. Okay, so now we can make the delta x go to 0, right? Because we're trying to build up a different differential equation. So then we're going to have minus Vx dd dx is equal to Krd minus Kdl. And further, we know that the dx is equal to Vx dt. Okay, so we can plug this relationship in. We're going to have dd dt equal to, if we move the minus sign here, that's going to be kdl minus krd. Okay, is that clear enough? Basically, from this PFR assumption, we can derive this differential equation that's describing the oxygen deficit in this river as a function of time. Okay, so again, you can see that Kd here is the deoxygenation rate constant, while L is organics remaining in the river water. Okay, the Kr is the reaeration rate constant, and the D is the oxygen deficit. So we have to note that the variation rate is proportional, or this rate is proportional to the oxygen deficit, right? Because the higher the oxygen deficit means that the lower the dissolved oxygen concentration, and there will be a higher flux or higher rate of this reaeration in the river water. Okay? So now we have constructed this differential equation. How do we solve that? So to solve for a differential equation, once we have this equation, we need to know what is the initial condition, right? And specifically for this initial condition here, it is because of the mixing of the river water upstream of this pipe, and also the wastewater that's coming from this pipe here. So what we can do is that we can define a dA here. So basically at the initial time, the oxygen deficit is equal to dA, while at the initial time, the concentration of the organics is equal to LA, okay? And further in this differential equation, we know that the L, we solved for that in our last class. Basically, L is equal to LA multiplied by exponential of minus k dt, okay? So this is basically solving for this remaining organics that's in the water due to the oxidation by the microorganisms, okay? So we have these initial conditions. You can see that we basically have three equations, right? We have the differential equation, we have these two boundary conditions. How do we solve for the D here? Okay, so I think in your calculus, you might have already solved this process, but as you can see, the solution to this differential equation is actually quite complex, and I don't want you to memorize the equation to solve for that. So because of that, I'll guide you through the derivation of this process, okay? So you can see that in this equation, we have several exponential terms, or we will have several exponential terms. For example, the L is a function of time and contains the exponential of minus k dt. And then at the same time, in this differential equation, there is a minus krd term. Normally, if we ignore this term, let's say if we ignore this term, and then the d is going to be containing an exponential of krt term, right? And because of that, let's make an assumption. Let's say that the d can be represented by a multiplied by exponential k dt plus b multiplied by exponential krt plus c, okay? So let's assume that this oxygen deficit is composed of three sections or three components. What we need to do is to just solve for the A, B, and C. So we have three unknowns, three equations, right? So now let's try to plug in and see what we can get, okay? And further, for simplicity, let's make a substitution. Let's assume that this term is now called x, and this term is now called y. Okay, so basically, this is giving us ax plus by plus c. Okay, so let's see what happens on the left-hand side. So left-hand side, we have dd dt, which is going to give us a or minus a kd, because the derivative of this x term here is going to give us a minus kd term. Okay, that's providing us the x. Okay, and also if we take the derivative of this term, that's going to be minus b kry. And for derivative of c, which is constant, that's going to be equal to 0. Okay, so on the right hand side, let's see what happens. So we have kd multiplied by l, which is equal to kd la. And then for this exponential term, that's x. Okay, and for the second term, let's see what happens. Okay, so second term we have minus kra multiplied by x minus krb multiplied by y minus krc. Okay, so now we can do a combination, because for a differential equation, these terms contain a time term here in the exponential term. So what happens is that the coefficient in front of these x and the coefficients in front of these y here should be equal. Okay, so if we compare the left hand side and right hand side, you can see that the constant term is equal to 0, and this means that simply means that the c is equal to 0. Okay, so now if we look at or try to track the x, you can see that so minus a kd should be equal to kd LA minus kra. And this is giving us a equal to kd LA divided by kr minus kd. Okay, so we got the first coefficient ready, and we got the last one ready. Okay, so what about the b here? So for the b, what we can do is that we can plug in this these three coefficients and then use the boundary condition. Okay, so we have dA equal to a plus b plus c. That's when time is equal to 0, right? And then we know that c is equal to 0 and a is equal to kdLA minus kr minus kd divided by kr minus kd plus b. Because of that, b is equal to dA minus kdLA divided by kr minus kd. Okay, so now we have solved everything. We have b ready, we have a, and we have c, which is equal to 0. So now let's plug into this equation. That's going to be a, or this kd LA divided by kr minus kd exponential minus kdt. Okay, you can see that in terms of b, we have this same term here, kd LA divided by kr minus kd, right? So we can combine these two terms, krt, okay, and plus dA multiplied by exponential minus krt. Okay, so this is what we get from solving this differential equation, and you can see that it's exactly the same, right? This is a solution to this differential equation. Okay, so then you may wonder, what is dA and LA? So dA and LA, as we have learned earlier, is decided by the mass balance, right? So the concentration or the total mass of these dissolved oxygen or oxygen deficit have to be equal to the dissolved oxygen concentration that's coming from the wastewater and coming from the river water. So because of that, the dA can be calculated by the DOS, the separated oxygen, dissolved oxygen concentration minus the mixture of the dissolved oxygen concentration. You can see that it can be separated into the wastewater and the river water divided by the total flow rate. And in terms of organics concentration, we can use the same equation to calculate that, by separating into the wastewater and the river water and divide by the total flow rate that's coming from these two streams. Okay, so you can see that this is our final equation that's describing the dissolved or the oxygen deficit as a function of time. So again, we should notice that here we're assuming that the BOD is entirely coming from the carbonaceous BOD. But if there is nitrogenous BOD, then they're going to have a separate reaction that's coming from the deoxygenation, right? And we call that rate constant as Kn. So you can see that the equation is getting more complex, but still you can see that in the final solution of this D, you have terms of exponential to the minus kdt, exponential to the minus krt, and exponential to the minus knt. So basically it's still three linear terms overlapping or adding up together. So we can use the same method to solve for this equation. But this is getting more complex, so I'm not going to cover that in the class. So with this equation here, we can basically calculate the dissolved oxygen or oxygen deficit at any location downstream of the emitting point, right? So here we have an example. Let's say we have a city that's disposed or emitting 1.05 cubic meter per second of treated sewage. So the BOD, or the ultimate BOD, we have this value, and then we still have some of the dissolved oxygen, and that's emitting into the river. And upstream of this outfall, the river has a flow rate, all right, and a velocity here. And also at this point in the river, it has a relatively low BOD and relatively higher dissolved oxygen. So based on this relationship, we can basically calculate what is initial oxygen deficit, right? So we know what is the saturated dissolved oxygen concentration. We know the flow rate that's coming from the sewage or the wastewater, and also the river water. We have the dissolved oxygen that's coming from wastewater and river water, and we can calculate what is the total flow rate. And same for this BOD here, okay? And then, so also it provides us the saturation value of the dissolved oxygen. So it provides us with the KD and also the aeration rate. So we can also assume that there's a complete mixing and the velocity in the river is the same upstream and downstream of the outfall, okay? So the velocity is basically the same. So from this relationship, let's look at our final equation here. So we have the LA, right? It's coming from this equation here. We can directly plug in the BOD values. And then we can calculate, we have the LA, KD, all of these as a function of time, right? And then first it wants us to calculate what is the oxygen deficit and BOD just downstream from the outfall. And this is by mass balance, we can directly calculate that. And what is the dissolved oxygen 16 kilometers downstream? Okay, so you can see that when we try to calculate this dissolved oxygen, you have to first calculate what is the oxygen deficit. But still in this equation, we're using time, we're not using distance, right? So this is where the velocity of the river water come into the picture, right? So by having this distance, which is 16,000 meters, we can calculate the time, which is S divided by V, 16,000 divided by 0.37, okay? So that's going to give us a value which is in second, and we cannot further convert it into day because all of these rate constants were provided in terms of days, okay? So this is an example in your textbook, and you can work this out and try to find out what is the dissolved oxygen. Okay. So as I have introduced earlier, the dissolved oxygen concentration will have a lowest point because of this Sag curve, simply because at the beginning the oxygenation rate is so high, it's consuming a lot of the dissolved oxygen, and the rate of aeration is small compared to that process. And as the organics are being further dissolved or further oxidized, the rate of aeration start to be higher compared to the rate of the deoxygenation. So that's going to increase our dissolved oxygen concentration. So how can we find this lowest point? Okay, so in the calculus, we know that for these extreme points or the critical points, one thing we can do is we can take the derivative and find and basically set that derivative to be 0, and then we can solve for this special point, right? So it turns out that for this critical point, it corresponds to a critical time that's having this lowest dissolved oxygen concentration, and that can be calculated from this equation, and we can further calculate what is the oxygen deficit at this critical point, and that's calculated by this equation here. Okay, so I won't further derive these equations here. So if you're interested, you can just use this equation and then take its derivative to 0 and then solve for what is a t. Okay, so now let's do a quick quiz. Okay, so what is a critical point? So the critical point is defined as which of the following? So it's either the point has the highest BOD, or the point has the lowest dissolved oxygen, or the point has the slowest water flow, or the shallowest point. Should be B here, right? So lowest dissolved oxygen. And this is also the reason why when we talk about the water quality management, we don't want to look at what is being emitted here. Although this is also very important, we basically want to look at this lowest point. We want to make sure that the dissolved oxygen are not completed or depleted at this point, because once they're depleted, even these microorganisms won't be able to survive, right? They won't oxidize the water, oxidize these organics anymore, and the water quality won't come back. Simply because even though if you have more oxygen coming into the picture, microorganisms won't have any oxygen to survive. Okay. So in terms of the river quality management, what people do is that they will typically set up a minimum dissolved oxygen to protect the aquatic life, and then you can reduce the LA or the BOD by the increased treatment, right? To reduce the BOD of the sewage. You can increase the DO by aerating the wastewater. You can bubble through or create some turbulence in the wastewater. Also, you can aerate the river. For the rivers, people or the water quality management personnel will choose the late summer for the calculation. So why late summer? For the following 4 reasons. First, during the summer, because of the evaporation, there will be a low river flow. Okay, so the low river flow will give us a low dilution. As we learned that from our last class, that the lower we dilute it, the higher the BOD, right? During the summer, normally there will be a high BOD. And because of that, we're going to have a low velocity. And this is mainly because the velocity is going to determine the rate of the aeration. So if you see here, one thing that I forgot to introduce is that the rate constant of the reaeration is proportional to the square root of the velocity. So basically the lower or the slower the flow, the slower the reaeration rate constant, right? So during the late summer, the reaeration is also very slow. And during the summer, there's a high temperature, and the high temperature will result in a high oxygen consumption, which is the KD. And also, because of the high temperature, the saturated oxygen concentration is lower, okay? Because the higher the temperature, the lower the solubility of the oxygen, right? And this is going to give us a lower oxygen deficit, which simply means that the oxygen deficit is low enough that the rate of aeration is being affected, because we show that the rate of reaeration is proportional to the oxygen deficit, right? So that's why people will choose late summer to evaluate how well the water or the wastewater is being managed. Okay, so there are also other factors that are affecting the dissolved oxygen profile. For example, there are multiple discharge points or non-point source discharge, or also the physical conditions of the change. Okay, and so that's why people will divide the river into reaches or different stages. For example, if you have a river and then you have multiple emitting points, then we're going to evaluate for different sections. There are also organics in the sediment. These organics are going to consume the dissolved oxygen. And there are aquatic plants. They can produce oxygen under sunlight, but they'll consume oxygen at night. And also they will grow faster in the summer because of the low flow. Okay? And when these aquatic plants die, they settle onto the bottom and they will form these organics. So they will further increase these oxygen demand. Okay, so these will all affect the dissolved oxygen in the river water. So it's not as simple as what the Sag curve describes, but that is already a mathematical or more scientific way to describe the water quality in rivers. And also we need to consider about the effects of nutrients on river water quality. For example, nitrogen and phosphorus, they can cause excessive plant growth and further cause the eutrophication. Okay, so for example, the effect of nitrogen, they're going to generate a lot of these negative effects that's affecting the water quality. An effect of phosphorus is going to cause a eutrophication and also produce these toxins and consume oxygen. Okay, so in terms of the management strategy, we're going to control the and discharge of these nitrogen and phosphorus from different sources. So now we can quickly go over the water quality management in lakes, estuaries, and oceans. Okay, in terms of the lakes, the phosphorus is a limiting nutrient. We have to memorize this. Okay, the phosphorus is a limiting factor. So the more phosphorus we put into the river or put into the lake, the more eutrophication we're going to see, or the lower the water quality will get. So the phosphorus can come from the following sources. For example, the natural sources, we're not able to control that. It can come from the municipal and industrial wastewater, detergents, septic tank, seepage, agriculture runoff. So to control the phosphorus, we have to reduce the inputs, add alum to alum, basically alumina, to precipitate the phosphorus, or we can use dredging. Okay, so you can see that the phosphorus will cause a lot of these algae to grow on the surface of the lake. So first, they will cover the sunlight and basically reduce the oxygen that's generated in the lake water. And once they die, they will form these organics and further form these sedimentation. And these organics will serve as a BOD in the water. And this is going to significantly reduce the dissolved oxygen in the water. Okay, so that's a burden to the water quality. So some of you may say that, oh, these look green, right? There must be a lot of photosynthesis taking place. But as a matter of fact, it's not. So once they call these, they also call these large coverage as the algae bloom, where the algae basically covers the entire water surface. This is going to affect the lives in the body of the water, and especially for the lakes. This amount of organics in the water is going to stress the oxygen demanding, or they're going to form these oxygen demanding species, right? And it's going to stress all the living organisms in the water. And there are different sources of this cultural eutrophication, right? They can come from the detergents. You can have the natural runoff, maybe from the rocks that's containing phosphorus. It can come from the discharge of the treated sewage, or the dissolving of the nitrogen oxides coming from the combustion sources. Some other sources, let's say from the constructions or runoff, manure runoff, so on and so forth. And in terms of the lake water quality, the acidification is also a very important parameter that we have to consider. So the acidification can be caused by sulfur and nitrogen oxides. They can come from the rain, fog, or snow. Basically, it's acid rain, right? They can kill the fish. And lake may have some buffering capacity, because we introduced earlier that there are a lot of carbonate and bicarbonate ions in the water, so they can handle these acid rain. But still, if we create a lot of these acidic species, they're going to kill the capability of the buffering species in the lakes. And also, we need to know that the calcium carbonate that's coming from a lot of the stones can also consume these acid. So this is further creating us some buffering capacity there. And in terms of the estuaries, these are the areas where the freshwater and seawater meet. So it can be bays, lagoons, harbors, and inlets. So there can be a lot of nutrients coming from the riverside or the freshwater side, right? So you can have let's say phosphorus or nitrogen that's coming from the river, and they will mix with the species in the seawater. So it can cause the fish disease, algae blooms, low dissolved oxygen, and also reduce the growth of the underwater grass. So they can impact the animal activity and also coastline erosion. So for these estuaries, we also need to consider about the pathogens, right? The toxic chemicals, and also the non-native species, because this is where the water mix and they might create a lot of burden in terms of the ecosystem in this area. And one famous example is the Gulf of Mexico, and people also call that as the dead zone. And this is because of a lack of the water management that's in the estuaries. Okay. In terms of the oceans, oceans have a lot of ecosystems, right? So one important participant of the ecosystem is the coral reefs, and we heard a lot of stories about how the global warming is affecting the coral reefs, and also the human. More importantly, is the marine pollution that's affecting these lives. Okay, and the pollution coming from the oil pollution, ocean dumping, or the mercury issue will also affect the quality in the oceans. And further, in terms of the groundwater quality, we need to know what are the sources of this contamination, right? So for the groundwater quality, for the groundwater, they can be affected by the improperly operated septic systems or leaking of the groundwater storage tanks, right? So in the introduction, we talked about how the oil or the gas in California as containing certain chemical species might affect the water quality in groundwater. And they can also get affected by the improper disposal of the hazardous wastes, spills, accidents, right? Leaking dumps or landfills, and also leaking retention ponds or lagoons. And in terms of the transport of these contaminants, we need to basically know a very simple equation. So typically these contaminants will just flow with the groundwater, but because of the absorption, that's by the sand or by the soil in the water, some of these chemicals might get retarded. So that's why we define a retardation coefficient, which is basically the flow rate of the water divided by the flow rate of the contaminant, or we should say that the velocity of the water divided by the velocity of the contaminant, and the velocity here are actual velocity or the linear velocity. So the higher the retardation coefficient, then the slower the contaminant will flow with the water, right? So we can go through a simple example here. Let's say that there are two houses, right? One house is emitting some contaminants into the groundwater. Okay, so the linear velocity of the water is 4.7 multiplied by 10 to the minus 6 meter per second. The retardation coefficient is 2.4. So because of these two parameters, we can calculate what is the linear velocity of the contaminant. That's directly 4.7 multiplied by 10 to the minus 6 divided by 2.4, right? So it asks us the time that's required to reach the second house. So we know the distance. We can divide the distance by the actual velocity of the contaminant. Turns out it's around 354 days. Okay, so that's all for the contents of this class. So let's try to review some questions. Okay, so how do we increase the dissolved oxygen and improve the river water quality? So we also learned about the dissolved oxygen Sag curve, right? So how can we solve for the final equation that's describing the time-dependent oxygen deficit in the water? Okay, so why do we choose the late summer condition to manage the river water quality? What factors other than point source discharge will impact the river water quality? And what are the important nutrients in the water, right? In terms of lake, estuaries, or oceans, what are the major factors that we need to worry about? And what are the major pollution sources of the ocean? And what is retardation coefficient of a pollutant in the groundwater? Okay, so I would say that this class contains quite many mathematical derivations on the oxygen deficit, right? I really want you to know about how we can how we can derive these equations instead of memorizing those complex equations. And we also introduced in general what are the pollutants or what are the processes that's affecting the water quality in different water resources. So that's all for the contents of this class. Let me know if you have any questions. Thank you.